All right, so let's go back to counting the cardinality of the union. Okay, so recall, we already talked about it. So the idea is if we have two sets, so let this be my universe U. So I have universe U, and I have two sets A and B. So set A, set B, right? Then A union B, the size of A union B is same as size of A plus size of B minus size of A intersection B. Yeah, why is that? Because when you do size of A, this set is counted in A, right? When you count the size of B, then this set is again counted in B. So what is common is getting counted twice. So you have to remove it once. So this is a so-called principle of inclusion exclusion. All right. Now we can extend it with three sets. It's actually more interesting. So let's look at this problem from the three set perspective. So we have what? Let's say, let's again go about it. So let's take our universe. So this will be my universe U. Okay. Then I take three sets. So let's take set A. Let's take set B. Okay, set B. And let's take set C. Okay. So this is our, and then we are asked the following. So this is my A, this is my set B, this is my set C. Okay. And then we are interested in what is the size of A union B union C. Okay. So now let's try to do this. So this is going to be, so first we'll relate it to size of A plus size of B plus size of C. All right. So we have added all these sets together now. All right. Now, what is the problem? So I'm looking at, say, let's look at A and B, right? So what was common to both A and B got counted what? Twice. So let's remove that, okay? So minus A intersection what? C. Then same thing for B intersection C. And then what is the other intersection? C intersection A or intersection C. All right, so you remove that. But in that process, actually something got removed three times, this part here. Okay, so it will be adding this again. So it will be addition of A intersection B intersection C. So this is the inclusion exclusion for three sets. All right. You can extend this idea for n sets. Yeah. So for n sets, it will be you add all the sizes, then minus two intersections, plus three intersections, minus four intersections, plus five intersections. And this is how it goes. Okay. And this is a generalization of inclusion exclusion principle. All right. But we are happy with two. And at most, we are interested at most in three. So this is the idea behind inclusion exclusion. And let's try to go about it now. Next thing we want to talk about is the analytic probability. Okay. So what is the probability? So basically, in probability, you have collection of events. So suppose you have an event space, or say suppose you have a sample space where you're tossing a coin. Suppose, okay. Now you're tossing a coin. You get head, or you could get tail, right? Now, what are the chances of getting an head? Yeah, that will be the probability of getting an head. Okay. So generally, this is something. So let's talk about probability. So let S be a sample space. So you do an experiment. Toss a coin. Yeah. You toss a coin. Say, let's say, toss a coin. Toss a coin. So let my experiment be. So let my S be, say, I toss a coin. So S could be head or tail, right? This is a sample space. Yeah. Then you're asking what is the chances? So what is the probability? So let's say A, which is a subset of S, an event. So let's say this be an event. Let's take our event to be basically a head. Yeah. And the question is, what is the probability of getting what event A happening? So probability of event A happening is what? Size of A divided by size of sample space, which is going to be what? Size of A is what? 1. Size of sample space is what? 2. So probability of A happening is what? Is basically 1/2. Is that okay? Yeah. So this is the idea behind probability. Let's look at some more examples. Suppose we roll a dice. Roll, say, a 6-sided dice. Twice. Okay. Yeah. And let's say basically this dice is the dice is what do you say, unbiased dice or fair dice. Okay. Right. I mean, if it is not, like, say, if you take a square and cut it, like, into really thin shape like that, no matter how you throw, it's gonna land either in the top or bottom, right? So that's not a fair dice. A fair dice means what? All the numbers are likely. Okay. So let's roll a 6-sided dice, fair dice twice. Okay. Note that dice is labeled from 1 to 6. Okay. So you basically have a dice, and then you have a dice where there's labeling. You can have 1, 2, 3, then other side will be 4, 5, 6. Okay. So this is the dice we're talking about. You could have an 8-sided dice too. I mean, you could have like 100-side dice as well. Okay. So yeah. So suppose roll a dice, fair dice twice. Yeah. So now what is the sample space in this case? So sample space is going to be, so what is my sample space? So, well, I mean, I'm rolling the two dices twice, and now and look at the outcome. Look at the number, the two numbers on top. Okay, because we could measure anywhere, really. I mean, you could also say, oh, I'm looking at the number which is at the bottom, hidden. Yeah, right. I mean, so just to make things fair, we are rolling two dices and we are looking at the numbers. We are rolling one dice twice, and we are measuring the numbers which come on the top. Okay, so that the experiment is clear to you. So what is the sample space? So sample space is going to be, if I want to list the sample space, it's going to be what? 1, 1. That means first roll I get what? First roll, and this is on the second row. Make sense, right? 1, 1 should be 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Okay. Then similarly, you'll have what? 2, 1, 2, 2, and so on. Okay. Then 2, 6. And then the last line will be 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Okay. This is my sample space. All right. Yeah. Then the question is, suppose, what is the probability? So let's talk about the event now. So in this case, let's call this sample space to be S. What is the size of S in this case? 36, right? First one has 6 options, second one has 6 options. So 6 times 6, so size of this is 36. Yeah. Now we can ask questions about various different kind of events. Okay, so first of all, event A. Event A be the event at least one of the numbers is 1. Yeah. So let's look at this event, for example. Okay, so what is the case that at least one of the numbers is 1? Yeah. So in that case, you can see, well, I mean, all of the first one will have what? 1, and all of these guys will have 1. So total is 6, and then 6 here, but 1 is common. So in total, that's what? 11. So size of A is 11, right? And then in that case, I can say, what is the probability of A happening? This means what? What is the probability that what? That at least probability that one of the number is what? 11. So let's ask this question. I want to basically ask this in words as well. So what is the probability? Let's write that down. What is the probability what is the probability that at least one of the numbers rolled is what? Rolled is 1, right? So, and what is that probability? That probability is simply going to be size of event A divided by size of sample space, which is going to be what? So 11 over. So this is my probability of event A to happen. Does that make sense here? Yeah. We could have given a simpler example. Suppose I roll a dice once. What is the probability of getting an odd number? It's basically what? 3 of them are odd. Total size of sample space is 6. So 3 over 6, which is 1 over 2. Okay. Then we can have different kind of questions being asked here. So suppose we have what? Let's take event B, that sum of the numbers rolled, and by rolled I mean the numbers on the top. Okay, we don't want to repeat the same thing. Some of the numbers rolled on top, rolled is say 7. So sum of the numbers rolled is 7. So what is the probability of such thing to happen? Okay. So then in that case, either you list down B. So we can list down B as well. Although if you're doing this event, say if your sample space is really large, and if your event space is also large, then it doesn't make sense to list down all the elements. Then all our counting methods will come handy. But in this case, we can do this, right? So let's write it down. So when do you get basically, when do you start getting what? 7. So when you have 1, 6, right? Or you have what? 6, 1. Okay. Then you have what? 3. Then we have 2, 5, 5, 2, right? Then we have what? 3, 4. We have what? 4, 3. And then rest of them are taken care of. There is no other possibility because 5 onwards is appearing already here. Okay. So these are all the cases where the sum of the numbers appear on the top will be what? 7. So what is the probability of B happening? Again, probability of event that sum of the numbers which shows on the top is what? Is 7. This is going to be size of B divided by size of the sample space is going to be, so 1, 2, 3, 4, 5, 6, 6 over 36, which is going to be 1 over. So this is the probability what of what the event that the sum of the number rolled is what? Is 7. Okay, and then you can have similar kind of questions. We could have seen that easily if we are more. We could have also seen it from the if we drew this nicely, but you don't have to do that. Yeah. And then there are other ways to look at the problems as well. Like you can say, what if I roll the same dice a million times? What is the probability that sum shows up to be 1,000,005, for example? You see what I mean? So there could be many different events, and the idea is to count things properly. So here, if you look at this, what are the techniques used? So techniques used are from the chapter 1 about counting, and the second one is inclusion exclusion. Those are the 2 techniques used. Because if you look at this problem, again, I'm slightly talking it loosely, and I'll make it more concrete later. You see, when we said, oh, what is that? At least some of the numbers is 1. This was actually what? This was set A, this was set B. And we're counting what? A union B, some sense. All right. If you get that, that's fine. Otherwise, we'll discuss this problem more. Now let's look at the following problem. So there are 35 people and 2 names are drawn at random to win 2 identical prizes. What is the probability that 2 specific people, Alvin and Betty, are both chosen? Okay. So the idea is that Alvin and Betty both are chosen. So let's basically think about this problem. So how would we go about it? So, and you're choosing how many people out of it? So the sample space is what? Sample space is all possible combination of 2 names, right? Do you agree? Yeah. So suppose there was Jack and Jill, so it will be Jack, comma, Jill, Jill, comma, and the order does not matter. Do you agree? Because we are choosing two names and the prices are identical. If the prices were different, then the order would have mattered. But since the prices are not different, our order does not matter. So out of 35, we are choosing what? 35, choose 2. Do you agree? That is your what? That is your sample space. Okay. Now, what is the probability that two specific people, Alvin and Betty, are both chosen? Now, how many ways can that happen? So you have basically, so let's say, let this event be, let's call this event. You want to give it an event name. Let E be the event. That Alvin and Betty both are chosen. So now we are interested in what is the size of E. So E is simply basically what? Size of E is 1, right? There's exactly one way to choose both of them, right? Yeah. So, and also there are other ways to see this, but then you can say probability of what? Event E, that Alvin and Betty both are chosen, is what? Size of E divided by size of S is going to be 1 upon 35 choose 2. And whatever that number is, we don't care about it, right? Yeah. Does that make sense to you? Yeah. It's a very small number, but it is what it is. Okay. Now, another way would have been we could have started thinking about we could have basically broken it as two events. So, event A, that Alvin is chosen, right? Event B, such that Betty is chosen. So, A, Alvin chosen. Event B, what? Betty is chosen. And when we say A, both, and when we say and, it's what basically? It's an intersection, right? What is common in both of them? Exactly 1, because we are choosing two people, right? So it could be, say, suppose there's a third guy, Jack. So Alvin and Jack can be chosen. Alvin and Betty can be chosen. And similarly for Betty, Alvin and Betty can be chosen, or Betty and Jack can be chosen. And there is only one thing which is common in both of them. Make sense to you? So this is the space you're interested in. So the intersection is just 1. Does it make sense to you? Yeah. So that is the idea behind it. All right. So now the question could be different. What is the probability? The question, I can change it now. I can say, so let's just have a variation of this. What is the probability that Alvin or Betty are chosen? So let's have a different question and let's ask this question ourselves. What is the probability that Alvin or Betty is chosen or chosen? Or is chosen. Is better English wise, but okay. What is the probability that Alvin or Betty is chosen? In that case, what are we looking for? We're looking for A. A be the event that Alvin is chosen, B be the event that Betty is chosen, right? So it's gonna be what? A union B. So this is what the probability we are looking for. We agree? Yeah. And that is what? That is size of Alvin, size of only Betty. So size of Alvin chosen, size of Betty chosen, minus size of Alvin. This will be what? This is my A, size of A union B. Do you agree? Yeah. Let me make a partition here. Here I know already by the formula itself, I don't need to do anything. I'll be n of A union B, or size of A union B, divided by total sample space. So now we need to find out what is the size of A union B. All right. So what is size of A union B? So what are the chances Alvin is chosen? So now Alvin is chosen, that is fixed 1, right? Now, how many options are there for the second person? 34. Do you agree? Yeah, yeah. So any of those 34 can be chosen, right? So size of A is what? 34, or 34 choose one, as we said, right? Do you agree? Because it's about how many ways are there that one of them is Alvin. Yeah, one of them is Alvin. That means second one has what? One is fixed. So the second one has basically 34 options. All right. What about similarly, size of B is going to be what? 34 as well, right? That Betty is chosen as one person and the other person has 34 options. So it's basically, as you said, 34 choose one or 34, they are the same thing. Okay. Now, what about A intersection B? Exactly what? One, right? Because we said, okay, there's exactly ones that they are basically both chosen, right? So therefore, this size of A union B is going to be 34 plus 34 minus 1. Yeah, which is what? 78 minus 1, which is 77. So this is going to be 77, right? This is same as, sorry, my bad, 68. Huh? 68. So 68 minus 1, 67. 67 divided by S, which is going to be 35. So this is a probability. All right. Does that make sense to everyone? Anyone who did not understand this, please ask. That it is precisely 34 choose one, right? Because out of 35, you already choose one of the guy. Captain on the side, he's fixed. He's Alvin. There's no other one. And then the second one can be filled in what? In 34 choose one way or 34 ways. Okay. And since there's no ordering, we don't care. Yeah, that's the idea. Okay, now let's look at the next problem. Suppose 35 people are chosen and two names are drawn at random to win the prize. What is the probability that neither Alvin nor Betty are chosen? So neither of them show up. Okay, so let's see how we'll basically make sense of that. So please think about the problem. So what does it say? It says basically neither Alvin nor Betty, right? So you have what? So A union B, or let's say A union B. What is the meaning of A union B? Please be precise. Huh? I mean, like, there's no need for throwing in the words. A or B. That is the right way to think about it. Yeah. When you say A union B, it is either A or B. Yeah. That is when you see union, it's or, period. When you see and, it's an intersection. This dictionary should be clear. You don't want to use any other language. It doesn't matter. All right. The first dictionary should be when you see a union is or, intersection is and. Okay. Yes. So that dictionary should be clear to us. So when you're saying A union B, you're saying what? It's either Alvin or Betty. One of them will show up. Do you agree? That's a union. Now, what is the complement of this? So what is the complement of A union B? Let's try to understand. So A union B is either Alvin or Betty show up. The complement would be neither of them show up, right? Do you agree? Yeah. So A complement B is basically exactly the event you're looking for. Neither Alvin nor Betty are chosen. Okay. So now, how do we count A union B complement? Okay. So note that the following. If you take a set A, any event, doesn't matter. Let's just take event E. Event E union E complement is going to be what? The whole sample space. Yeah. You agree with that? Yeah. Because, well, I mean, if either thing can happen or not happen. And this will exhaust all the possibility of your all possible outcome, right? Like say, if you toss a coin, it's either head or not head, which is tail. Yeah. Or if you throw a dice so if you throw a dice once and you say, okay, it's either odd or not odd, then it's even. And then that's going to be all the space. Okay. So A union A complement is going to be the whole space. Is that okay? And also, not only that, what is size of A union? So also another thing is that size of E complement is going to be the total size of sample space plus, sorry, minus size of. Okay? Size of the complement is what? You remove that possibilities for E, and whatever you get is the size of the whole thing. Is that okay? Yeah. There's an analytic way to prove this, but analytic way of proving this is not very, what you said, not very illuminating. But if you want, we can analytically prove it. Well, analytically proving would be what? Let's just try to see. Well, if you look at E union E bar, it's going to be S. Do you agree? Yeah. Now, what is takes a size? So size of E union E bar is going to be size of S. But what is the size of union of two sets? It is basically size of E plus size of E bar minus size of E bar, E intersection E bar. And that is size of S. You agree? Yeah. This is using the law of inclusion exclusion. But we live in a Boolean world. Our logic is Boolean. Our sets are also Boolean. Either you are there or you're not there. There's no other possibility. Yeah. So there's no intersection where you will be there and not there. That's not going to be there. So this is what? This is 0, right? So if you take any event, E, and you add the size of E and E complement, you'll always get S. Yeah. So we'll say, well, what's the point of all this? The point of this is that you get actually quite a nice result here. So divide throughout by S. If I divide by size of S, size of S, size of S. Yeah. What is this? This is probability of what? E complement. Yeah. Something not happening. This is 1 minus what? Probability of. The probability of something not happening is 1 minus probability of happening. Okay. Yeah. Does that make sense to you? Yeah. So, probability of, say, suppose you toss a coin once. Yeah. So probability of getting head plus probability of not getting head should be 1. Is that okay? And there are a few other things, huh? I mean, so now, so in this case, I want to know what is the probability of A union B complement. So I can quickly say that probability of A union B complement is going to be 1 minus probability of A union. Do you agree? The only reason why I'm going this way is because we have already computed what is the probability of A union B. So let's recycle that information, right? So it's going to be what? 67. So probability of A union B is 67 divided by 35 choose 2. So it's going to be 1 minus 67 divided by 35 choose 2. And this is it. We don't need to simplify it. We don't care about simplification unless you're really running something. You go to a casino and then you're trying to basically count the cards. And then you're trying to decide, oh, should I bet more or should I stop? In that case, you really want to, simplify and see what number it is, right? But otherwise, you can leave it that, rest is the calculator work. You could do slightly tediously too. The slightly tedious way would have been you say, oh, okay, A union B complement is basically size of A union B complement is size of S minus size of A union B. Yeah, you could have done that way as well. And then you basically talk about it. Okay, now let's divide by S. Let me change the color so that you know the next step is basically dividing by S, dividing by S, dividing by S. And this will simply become what? This part becomes 1, right? Which will give you the same result as we got here. Okay, so the idea is the probability of A plus probability of A complement is 1. Yeah, A, B, any event. All right. Now let's look at the following problem. You have 5 cards, poker hand. What is the probability that you receive exactly 1 pair? Let's think about it. So you have a 5 card, all right? And then you're asking, what is the probability that you receive exactly 1 pair? let's try to understand this problem first. So you have how many cards? You're choosing how many cards? 5 cards, right? Do you agree? And you're choosing it from one deck. You're not choosing from many decks. So you have one deck. So let's try to understand how does the deck looks like, okay? So just in case somebody who, who does not, has not seen cards, okay? So in cards, basically you have what? You have ace, which is number 1, right? You have A, and then you have basically all these number cards, which 2 all the way till what? 10, right? And then you have what? You have basically, you have king, you have queen, and you have jack. Yeah, whatever you call it, people call it Badshah, Rani Gulam, whatever, who cares what they are. But and then, so we have A to 10, and so these are the things for, there are 4 suites, okay? One is basically, one is given, so they are black and white, right? So, sorry, not black and white, black and red. So black has basically 2 of them, essentially. One is spade. The spade, basically, I'm not very good at drawing, so please, let's try to draw a spade. Somewhat like that. So this is spade. And then there's one with a club. Which is like it, like shaped like this. Yeah, these are filled. I don't want to fill them, but club. There are 2 black, right? And these spade, there are again 13 of the cards for spade. There are 13 of the cards for the black. And then there are 2 more. One is diamond, right? And then there is one more, which is heart. So diamond. So there are total of how many cards? There is total of 13. So 13 times 4, which is 52 cards in total. Okay, so now you want basically what? You want a 5 cards out of it, right? So how can you choose 5 cards? Basically, it's gonna be, so my sample space S is all the 5 cards, all possible 5 cards, right? The sample space S is gonna be, so S is simply 52, choose 5. Yeah, because we don't care about what? We don't care about, our concern is not what order, right? We just need 5 cards. So 5 cards as a set, right? Okay. Now, let's say E, again, it's a good idea to name the event. So let E be the event, what? Event E, that we receive exactly 1 pair. Okay. All right. So now, so we want exactly 1 pair. What do you mean by 1 pair? 1 pair would mean you have basically, say, 3 of, say, pair would mean basically 3 of same, right? So let's say 3 of diamonds, and say 3 of clubs, for example. Yeah. So this is what it means by 1 pair, and there's no more 3s. Yeah. Was that okay? And if there is an ace, so there is, suppose these are 2 cards, and if there is an ace, then there will be no more aces as well, right? The 3 other cards are different from each other, and they're also different from this one. That is what it means by exactly 1 pair. Do you get the idea? All right. So now let's count. Yeah. So let's see, what is the size of E? So first of all, let's say we want to make the pair. Yeah. So let's see, how many choices do we have for making a pair? So let's see. So we could have 3, right? 2 threes. We could have 2 aces. We could have 2 jacks. We could have 2 queens, right? Yeah. So we could have, like, so out of those 13, we need to choose 1. So 13, choose 1. to decide which of those pairs we are going to make. Do you agree? Yeah. Now you have chosen 13, choose one, and then you decided, okay, so when I say 13, choose one, I say, okay, let's say, for example, I chose to make a pair of ace. Okay. Now, how many cards are there for ace? There are 4 cards for ace. Do you agree? So then I can do what? 4 choose 2, right? Because out of those 4, I need to what? Get what? To the 2 of them, right? So I can have, say, ace of ace of club and ace of diamonds, for example, right? Or I could have ace of clubs and ace of hearts, for example, right? So it's out of 4, you're choosing 2, essentially. All right. So this is about choosing what? This is about choosing. So for other cards, I can now choose 3 of what? I can choose 12, choose 3. This will decide I'm choosing what? 3 what different cards, right? Value or denomination cards. And then for each of those, I have what option? How many options? 4 options. So I'll choose 4, choose 1 for all of them. 4 choose 1 times 4 choose 1 times 4 choose. Okay. So this is your size of E. Let's just make it more clear again. So I have 5 spots. Okay. Just trying to make this problem clear because this will. So let's see the first part. Again, these are not ordered. So I'm going to basically use what? Choosing argument, not permutation. Okay. So now these 2 are chosen how? So first you decide what of those, which of these kind I'm going to choose. So let's say 13 choose 1. And then once I choose what kind, then I will have what? I will have 4 choose 2. That will choose 2 cards out of those 4. Okay. Now then there are 3 more left. Yeah. And they have to be of different kind, right? So I'm going to do what? I can either do 12, choose 3. I choose the kind. And now for every kind, there are 4 cards. So I will do what? For each one, I will choose what? 4 choose 1 for the first one, 4 choose 1 for the second one, 4 choose 1 for the third one. Okay. So this is one way of going about it. Yeah. We could have also done it in a way, we could have broken it in a slightly different way. We could have done, okay, 13 choose. So you could have said 13 choose 1, 4 choose 2. And then you say, okay, for the third card, the option is what? 12 options. And for each option, I have what? 4 choose 1. Then for the second one, I have what? 11. And then I have what? 4 choose 1. Then for the next one, I have what? 10. I have 4 choose 1. But when you do 12 times 11 times 10, you have ordering in mind. So to remove that ordering, you divide by something, which is factorial 3. Okay. So that's why instead of doing this, I prefer doing this way. So I get, this is my event E. And then what do I get here? I get, so probability of E, which is our poker hand, with basically what? With exactly 1 pair is going to be size of E, which is 13 choose 1, 4 choose 2, 12 choose 3, 14 choose 1 to the power 3, the whole divided by what? What are we choosing? We are choosing 52 choose 4. So this is the, does that make sense?